All right. Just one second. Okay. So thank you very much for this opportunity. Um, as mentioned, I'll be talking about the simplicity of in correlators. So this is some work which is done in collaboration with Arthur Lipstein, Jaje May, Ivo Sachs, and Pierre Van Hove. And towards the end, I'll describe some more recent work in progress, which is almost done with the same set of people, except Pierre is replaced with Joe. Okay. Um, Very good. So let me start with a very broad motivation as to why we are studying this problem and what exactly the problem is. So as all of you know, scattering amplitudes and scattering, of course, is one of the simplest process that one can study in quantum field theory and quantum gravity. And in order to study a scattering process, what you compute are called scattering amplitudes. And these are directly related to physical observables that you can measure in experiments. Okay? Sometimes they're called the scattering cross section and so on. And one way in which we are initially taught the subject is via Feynman diagrams, and these are basically just diagrammatic rules for describing various terms in perturbation theory. And what these correspond to are essentially time-ordered correlation functions, along with something called an LSZ prescription that basically sets your external states on shell. And in order to exploit all symmetries of flat space, what you usually do is evaluate them in momentum space. You go to coordinates where you can basically, take Fourier transforms easily. And an example of such a very simple, but the slightly, the first non-trivial example of a Feynman diagram that you draw is perhaps for a 2-to-2 scattering, where you have some propagator, and as you know, it just looks like this has an expression of the following form, where you essentially get the coupling constant along with the inverse kinetic term. Now, while these Feynman diagrams are nice and it gets us through our QFT1 courses, often once you begin computing more and more Feynman diagrams, you realize that they're not the best approach to computing amplitudes. And this is because they involve off-shell particles. Of course, as you know, this particle is off-shell. And sometimes in intermediate steps, they have many spurious poles. So what I mean by spurious poles is simply the fact that in intermediate steps, there are certain poles which just cancel out after you add every term in the Feynman diagram. And this process of adding every term in Feynman diagrams often involve very heavy algebra. And this thing is not so apparent when you're computing low point functions. Like, let's say if you're just computing a 4-point function, is not all these problems are not very apparent. But if you're trying to compute higher and higher point functions, then it gets worse. I forgot to mention, but feel free to interrupt me at any point of time. Okay. Good. So now just to give you an example of some very simple process, if you just wanted to study the 2-to-2 scattering in Yang-Mills, then you would essentially draw 3 diagrams with some subtlety about color ordering and so on, but it's roughly of this order, where you have some S channel, a T channel, and some cross term that you can write down. And this is not too difficult to compute. You can just do it by hand, perhaps in like 5 minutes or something. And it's often an example in a QFT course. But soon the number of diagrams increase and handling them gets very complicated. So let's say you wanted to evaluate a process involving 5 gluons. So a 5-point scattering, you would have to sum over roughly 25 diagrams. And then if you have to do a computation for a 6-gluon scattering, you have to sum over 100 diagrams. And that would also involve diagrams of different topologies. For example, you can have Feynman diagrams of this kind, where everything is, all the propagators are linear, or you can have diagrams of this kind, where basically propagators look like drones or something, and many others, of course. In fact, this 6-point amplitude was first evaluated by Park and Taylor in 1985. And this constituted of approximately 220 Feynman diagrams, which, as you can imagine, resulted over hundreds of pages of computation. And at the end of the paper, in fact, the paper was not too long. It was around, I think, of the order of 10 pages, and all the 10 pages constituted of various matrices, which eventually led to the final answer. And what they mentioned was, and just an excerpt from their paper, is that we hope to obtain a simple analytic form for the answer, making our result not only an experimentalist, but also theorist delight. And within a year, they actually managed to guess an answer. I think the way they probably arrived at the guess was to first see a structure at 4 points, 5 points, and then conjecture if a similar structure would work at 6 points. But they weren't able to actually prove it. And by prove, I mean, actually show that adding all the terms results in some simple form. But just to say you what this form is, I mean, this is basically a 6-point low on amplitude for some specific helicity configurations known as the MHV configuration. The details are not going to be important. And these variables roughly correspond to some dot products. So these are basically some dot products of momentum and are known as spinor helicity variables. But it's sort of nice that hundreds of pages of computation just gave you one simple term. And nowadays, it's known as the Park-Taylor formula. And so like I said, they basically guessed an answer and checked it numerically. But this was not the first time it had happened, although this example is often cited as one of the striking examples. Before this, in an old paper by DeWitt, when he was, in one of his famous series of quantum theory of gravity papers, when he computed the graviton 4-point function, there's a very similar problem. The 4-point function in gravity, again, is not very easy to compute, and it's not an example that you do in your QFT courses. And this is because the 4-point function often requires you to sum over 2,000 terms. And again, in this particular paper, David actually managed to do that heroic computation. And he again noticed that there were many cancellations which occurred. And the final expression was again very simple. And just to read out a quote from David Thing, because I really like this quote, which is that a large amount of cancellations between terms has to still be dug out of the algebra. And this combined with the final results being very simple leads one to believe that there must be an easier way. But this easy way was not found until quite some time. But it was eventually in the early 2000s with several heroic works, one of them being the BCFW formula. And this eventually led to what's known as the amplitudes program, as of course nowadays many people work on it. Now it's quite natural to ask whether such simplicities and adding various terms and seeing that you end up with simple results and so on, was this only a coincidence for scattering amplitudes, or is this something that also generalizes to other things? For example, one thing that we'll be interested in this talk and what the next the next slides are going to be about is what are called in correlators. I'll describe what they are, but roughly they are computations of operators at computations of correlation functions on a given time slice. That's the problem we'll be interested in. And just to give you a context about the difficulty people have been facing in computing these objects, I mean one example is that as of now we know of 3 different expressions for a 4-graviton correlator, and it's not obvious how they're related to each other. And in fact, we don't even have an explicit expression of an helicity amplitude beyond 4 points, even in Yang-Mills theory. And we barely understand loop integrals beyond some simple cases. So let me re-emphasize what we are going to be discussing in this talk. So we are essentially going to compute one of the simplest things that we can even think of and probably have studied in our QFT course, quantum mechanical course, which is basically the computation of correlation functions with operators inserted at a given time slice. Okay. Now, this is a problem that does not have time translational invariance. You could, of course, ask this in flat space itself, where you just take any state you like, which is denoted by psi, and you have some insertions of operators, all at some given time slice. And the spatial points are not important, so you can take a Fourier transform along that direction. And since the operators are inserted at a given time slice, you're clearly breaking time translation invariance. Sometimes these are also known as in correlators, because unlike an S matrix problem, where you go from a state at t equal to minus infinity to a state at t equal to plus infinity, here you're essentially coming back to the same state. You start with the same bra and you end up with the same ket. I probably said that in the reverse order, but anyway. And therefore, they're often known as in correlators. Good. Now, in this talk, just to keep things very simple, I'll describe the simplicity that we observed in for objects like this in flat space. So you can really just think of these as correlators in flat space, but you can map them to a problem or a computation in ADS or de Sitter spacetime, which is relevant for cosmology, by a simple Wild transform. So I can give more details on that, but but just to keep things simple, I'll just talk about flat space. And this also means that I'll not discuss examples with IR divergences, but I'm happy to discuss what happens in cases when you do have IR divergences. Okay, good. So this kind of a problem is interesting for several reasons, I think, but just to highlight two of them. When we are computing a correlation function like this, you first need to determine the state, which is often, it's sometimes famously called the wave function of the universe. And these are related to ADS correlators by analytic continuation. So in some cases, when you know the wave function of the universe, or you know the state you're evaluating things in, you essentially know correlation functions in ADS as well. So, and of course, for the ADS CFD community, this is of quite a lot of interest. And apart from that, these kind of correlation functions are precisely what are studied in cosmology and are known as cosmological correlators. Of course, experimentally, we haven't got slightest clue beyond the 2-point function as of now. I mean, sorry, I shouldn't say the word slightest clue, but we don't have an experimental evidence of things beyond 2-point functions. But it's essentially what's on the horizon for several people. So these are, I think, two very good reasons to study these. Okay, so now let me just give you a summary. So in case you fall asleep for the remaining part of the talk, let me just give you a summary for what we have achieved. I think the first point that we achieve is that we find a novel integral representation for these correlation functions in terms of the flat space S matrix. So I'll essentially give you a prescription by which you can take your favorite Feynman diagram in flat space, which are used to compute S matrices, and you basically compute an integral transform of that object in order to arrive at these inner correlators. So that's going to be one point. And the second point that I'll talk about would be, I'll give you some explicit examples for certain loop integrals. And what I'll argue is that the loop integral for the inner correlator have lower transcendentality than the wave function. And if you like, the statement can be recast as saying that loop integrals in de Sitter seem to have lower transcendentality for loop integrals in ADS. So this would be a broad summary of what the result of the talk is. Okay, if there are there any questions at this point? Okay, good. Okay, so now let me describe why this why this problem is difficult and what this problem is. So as I already mentioned, we'll be evaluating correlation functions of operator insertions at a given time slice. So you still have translational invariance along the spatial directions. You've broken translational invariance along time, but you still have it along the spatial directions. So we are essentially going to take a Fourier transform along the X, Y, and Z direction. And that's what I'm going to mean by momentum space. So when I say momentum space, I just mean the 3 momenta. I'll be working in 4 dimensions throughout the talk, but for most cases, that's not important at all. Okay. And like I said, we'll be interested in this object. And as you can imagine, you can express this in terms of a path integral by inserting a complete set of states, and it basically has a following expression, where these phi's are just insertions at t equal to 0. In fact, so you would imagine that if you were able to compute psi, or if somebody gave you what psi was, you would be able to compute this correlator. And for cases when you're working with something called the Hartle-Hawking vacuum, psi and these correlators at tree level look very similar. So they're not very different at tree level. And the one way to define psi for the when you're interested in the vacuum wave function, when you're interested in the vacuum state, is to define it by a path integral. So you can define psi as the following path integral, which is where you basically place some boundary conditions at t goes to minus infinity, and at t goes to 0, you tell how the profile of the field should look like, and you just evaluate this path integral. And by a saddle point approximation, this is nothing but e power is on shell. And that's why by an analytical continuation, these are often equivalent to computing correlators in EDS. This has its caveats when you have IR divergences, but that's not what I'm going to be talking about. Okay. So in case the path integral representation was not familiar, these wave functions also satisfy the Schrodinger equation. Since this is just a ground state wave function, up to some subtleties about normal ordering and vacuum energy being renormalized, etc., it essentially satisfies this equation. Okay. And a simple example, of course, is the example that we know how to solve, which is the harmonic oscillator, where the Hamiltonian takes this very simple form. Psi essentially has some form like this, which is a Gaussian. An exact similar thing also works when you uplift this thing to a free field, or sorry, to a scalar field. And for a free scalar field, we know the Hamiltonian takes a form like this. And then you can essentially solve this differential equation or evaluate the path integral, and you would end up with an expression of this kind, where you've now got to integrate over all possible oscillator modes at that given time slice. Okay, so this is what's known as the ground state wave function. Now, of course, if you have interactions, you would essentially solve this equation, using perturbation theory. You can either keep evaluating the path integral if you like, or you can solve the standard differential equation, and you would obtain a very generic structure which has a form like this, where these objects, the ones which are the coefficients of the fields, these are often called the wave function coefficients. So when somebody says the wave function, they might often refer to this object. And these are the objects which, by analytical continuation, are related to correlators in EDS. Okay. And evaluating these objects sometimes is described as what's called old-fashioned perturbation theory, and it's not covariant. And it's obviously not covariant because we have broken translational invariance. Okay. So while we know how to solve these equations using, while we know how to diagonalize a Hamiltonian and solve these in general from our quantum mechanics courses, we can also reorganize reorganize the evaluation of wave functions in terms of a path integral, which naturally leads to what are called Witten diagrams. And the only difference between a Witten diagram and Feynman diagram is that you now have a boundary at some particular time instant, right? Because all my insertions are at that given time. And since you have a boundary, you're led to two kinds of propagators. So one propagator that you have is what's called the bulk to boundary propagator, where one of the legs are attached to the boundary. And the other kind of propagators you can have are just what are called bulk to bulk propagators, where both endpoints are at the same time slice. And for example, if you were interested in computing the 4-point wave function coefficient, sometimes called the 4-point function, in phi-4 theory, you would draw a diagram like this. That's the contact diagram. And in phi-cube theory, you would draw a diagram like this. Now, while this might look like a loop level diagram, these are really just diagrams at tree level, because the thick line is just denoting the boundary at t equal to 0. And from the way the diagrams are drawn, it also manifests that momentum conservation is along the spatial directions only. Okay. Sometimes in the ADS literature, the same diagrams are drawn with a circle instead of a line. So that's it. Very good. So now just to give an example of how to compute these Witten diagrams, you first need these propagators. So the propagators which end on this time slice were called these bulk to boundary propagators. And in flat space, they have this very simple form, which is a plane wave. And this is exactly the same form up to some powers of time when you consider conformally coupled scalars in de Sitter. If you were to work with scalars which had a certain value of mass, then you would essentially end up with the same propagator. And a very similar thing is also true for the bulk to bulk propagators. The bulk to bulk propagators are now sums of two terms, where one term is very familiar, which is the standard Feynman propagator in flat space. And this other term is the one which breaks translational invariance and is required because you want fields to satisfy Dirichlet boundary conditions. Okay, so you can check that this propagator basically vanishes at t equal to 0. And this is this term which solves the homogeneous differential equation breaks translational invariance. That's it. So this is really the main difference between a computation in what you're used to doing for the S matrix and something like the wave function. Good. So now let me just describe to you the a simple example of the 3-point function or the 3-point wave function coefficient in phi cube theory. For that, you would draw some diagram like this. And you would essentially write a very similar expression as you would have done for the S matrix, except that you would cut the time integral off at t equal to 0. Along the spatial direction, you would still write the same integral you would. And since the integral at t is cut off at t equal to 0, instead of getting a delta function, you would get a pole in k1 plus k2 plus k3. Okay. And this thing, the integral over the spatial direction gives you the standard delta functions. So this is the first place where you begin noticing a difference between a S matrix calculation and the wave function calculation. Very good. Now, a very similar thing is also true when you consider exchange diagrams. I think this is the only slide where the computation is done in some details. And you would again just use the rules and you would write down a similar integral of this form, where you would now also have the insertion of the bulk-to-bulk propagator. And the bulk-to-bulk propagator, as I showed before, is a sum of 3 terms, where 2 of them look like the Feynman propagator, and 1 of them is the homogeneous piece. And you can evaluate the time integrals. You just evaluate them. You just put it on Mathematica if you like and just evaluate them. And they give you a sum of 3 terms. They basically look like this plus this plus this. But if you sum them up, you would find that the final answer is just one simple term, which is this guy. In fact, from the intermediate step, you might have believed that you would end up getting, the pole structure is of the kind that you get k plus k12, k12 plus k34, where the variables are clear from the picture. But you would find that once you sum them up, you actually don't get a pole that you see in the intermediate step. Okay. And hence that pole you could identify as a spurious pole. In fact, what's even nicer is that this answer can be written as 1 over k12 plus k34 times a product of contact diagrams, because we saw that the contact diagram was really just sum over k's. So in fact, these two guys, you could really just think of as product of 2 3-point functions. In fact, this example already suggests that there might be a recursive structure, although the recursive structure here is really diagram by diagram. So a 4-point diagram can be written as a product of 2 3-point diagrams. Okay. And you can actually evaluate this integral in a very different way without having to go through this brute force computation. But the very different way is not very complicated. It's something we all learn in high school, which is this integration by paths. And it was shown in in some papers by Nima, then Beninkas and Postnikov, that you have some very nice recursive structure, which they also exploited in order to write down some very nice looking polytopic structure. And this is not an accident. It's not an accident which happens for the simple example. This kind of a recursive structure is also present for spinning theories and for fermions, anything you like. Okay. Any questions or comments at this point?
But yeah, well, that recursive structure is only there because of your t equals 0 boundary.
I mean, in so it's not necessarily true that it's because of t equal to 0 or something. I mean, in flat space you have many recursion relations between S matrices, like you have something called the BCFW recursion, which effectively talks about relating an n-point amplitude in flat space, an n-point scattering amplitude, let's say in Young-Mills theory or something, in terms of n-1 point amplitudes. So for example, in this very first slide, I had described this formula here, which is the Park-Taylor formula. You could actually obtain this by using something called the BCFW recursion. And the BCFW recursion is a property of summing over all Feynman diagrams. And that, as you know, is not at any given time slice. That's something with some, like, that's an object which appears as a correlator computed between t equal to plus infinity and t equal to minus infinity. So in flat space, we have a lot of recursion relations like this. And in fact, for certain helicity structures, you can resum that recursion relation. But in here, it's something which is a diagrammatic recursion. And you're right that it's an artifact of cutting things off at t equal to 0. But it's one example of a recursion relation beyond S matrices. Okay. Okay. Very good. Good. So now, I've already, as we've already discussed, I mean, these kind of things have poles. And as we know, in flat space, the singularities of scattering amplitudes typically contain physical information. For example, one physical information that's often evident from a scattering amplitude is that at any physical pole, the amplitudes factorize into lower point amplitudes. And it's often said to be a consequence of unitarity. So it's natural to ask that what's the meaning of these poles that appear in the final answer for these correlation functions, and whether these poles for the correlation functions also contain any physical information. And the first thing you would notice is that for physical configurations of momentum, now if you remember from the last slide, all these guys are essentially sums of momentum, sums of moduluses of momentum. So for any physical momentum, you never have a singularity, because at best, the singularity for any of these can occur when everything becomes collinear. So you can only have singularities of that kind in physical momentum. But beyond that, you never have a singularity for momenta which are physical. So in order to see any singularities, you have to analytically continue the momentum. And one such important singularity is this object, where you essentially have the which is a singularity for all the where the sum of external energies goes to 0, and it's known as the flat space limit. And what the flat space limit does is it essentially restores translational invariance along time. So what I mean is, when we were evaluating these Witten diagrams, we had cut the integrals off at t equal to 0, which gave us these poles. But instead, had we continued the integrals from minus infinity to plus infinity, we would have ended up with a delta function in energy. So what I would like to do from the answer is to somehow restore the delta function from the 1 over E pole, where E is the total energy that enters the particles. And for massless particles, the energy of individual particles such as mod of Ki. So in this case, it's really this guy. And here, the way you restore this, or the way you take the flat space limit, is to evaluate the residue as this total energy goes to 0. And this is what gives you the flat space scattering amplitude. So in this particular diagram, you evaluate the residue as E goes to 0. So you take this object and you evaluate the residue here, and you would recover what you would call the Mandelstam invariant S. Okay. So in a way, the wave function of the universe already contains the scattering amplitude. So you can really think of all scattering amplitudes for any process you like, at least for massless particles, being contained in the wave function of the universe. Okay, and this flat space limit is often useful for performing several consistency checks, useful for bootstrapping the final answer without referring to any time integral, and so on. But this was just one example of a singularity. You also have other poles, and a similar reasoning exists for the physical interpretation of these other poles. So if you evaluate the residues at all these poles, you would find that the wave function always factorizes into a lower point wave function and an amplitude. But that's, I'm happy to explain that more, but it's not going to be relevant now. Okay, very good. So now let me explain how you can obtain correlation functions via the wave function. So as I already described in one of the early slides, the way you evaluate an inner correlator in some given state is to express it as a path integral of this kind. And since it's really one more path integral away from the wave function, you would naively expect that this object on the left-hand side is more complicated than individual wave function coefficients, since you have to really do one more path integral. And here's where we found a surprise when we did this last year, which was that as long as you're working with conformally coupled scalars in de Sitter, or if you like massless particles in flat space, you would find that at loop level, this object is much simpler than this object. And this happens due to many non-trivial calculations. And it's not something which is manifest from this formula. There are some formalisms like the Schwinger-Keldysh formalism and so on, which make this slightly more evident, but it's at this point we still don't have a proof that it must be simpler in every case. Good. Good. So now you could naturally ask as to why we study loops in this. Of course, apart from a natural curiosity, and this is and it's a valid question because loop corrections are not perhaps measurable anytime soon in cosmology. We still haven't measured the tree-level 3-point function, so it's still at a point where it's of theoretical interest. And in terms of theoretical interest, it's of course useful to ask this question because it provides higher order. It provides tests for ADS-CFT correlators at higher orders in N. And it's also of a mathematical interest as to what kind of functions would appear after you do the loop integrals. That's something which mathematicians have also been interested in for quite some time. There are several works on loop integrals and integrands. I might have missed some authors, but it's a relatively large community. And in the next few slides, I'll give an example for some loop integrals of the wave function coefficient and of the NN correlator, or if you like, loop integrals in ADS versus DS. Good. Good. Now, why is it difficult? Why don't we have more results than just a few of them? And this is because in flat space, when you're computing a loop diagram, you essentially have to integrate over things which are squares of momenta. So if you were to evaluate a bubble diagram in flat space, one of the first examples of loop diagrams one does in a QFT course, you would essentially have to do an integral of this kind. And when you have integrals of this kind, what you can do is use Feynman parametrization to introduce an auxiliary parameter and combine the two denominators into a single denominator. Or a similar thing is achieved by using Schwinger parametrization. But for the wave function, or for the NN correlator, a generic loop integral is not obtained from squares of momenta. Because as I described in the previous slides, you essentially get sums of mods of momenta. And hence a generic loop integral for psi might look like this, where you have sums of mods of momenta or just moduluses of momenta. And when you have objects of this kind, it's not easy to combine the denominators using Schwinger or Feynman parametrization. You would have to deal with this integral in some new way. And in fact, as far as I know, all explicit loop integrals till now in momentum space have only been computed when you have axisymmetry. So if you have the bubble diagram that has axisymmetry, you can do it in that case. There has been some recent progress on going to the triangle diagram, but it's but we still don't have an explicit form of the triangle diagram here. And just to give you a context, in flat space, of course, people have evaluated things to 6 loops and so on. But in here, we are still stuck at 1 loop. Okay. Good. So let me give you one of the only examples that's perhaps known to us, which is the example of a bubble diagram for the wave function. Say a diagram of this kind in 5-4 theory. It has the following long expression. Now, most of the long expression is not important, but the only thing to focus on is that it has dilogues. So as you know, dilogues are roughly one integral of a log. It has dilogues and log squares. And this is where you see that it has a higher transcendentality than the corresponding scattering amplitude. So if you were to evaluate the bubble diagram, let's say from Peskin and Schroeder, Weinberg, whatever your favorite book is, you would just find it's a log of momentum. But here you find that it's a dilogue. You could take the flat space limit of this object, and you would expect the flat space limit to essentially recover the same structure as in flat space, because with in fact the same UV divergence. This is because the UV divergence is independent of what space-time you're in. Right? Okay, but the takeaway point from here is that it's a dialogue instead of a log. Okay. Now you could ask what's the corresponding statement for the in correlator, for which, as you imagine, you have to take the wave function and then you have to compute one more path integral to obtain the in correlator. You can either do that or you can evaluate it using Schwinger-Keldysh. And what I mean is you essentially evaluate this correlator at second order in perturbation theory. You have to sum over several diagrams. You can write it in terms of the propagators which appear in Schwinger-Keldysh, or you could just evaluate the path integral and you would obtain some expression of this kind, where this psi4 2 just denotes really this expression, which is the 4-point wave function at two loops. The 4-point wave function at second order in perturbation theory. And these are some tree level expressions at first order. And this is just a result of that path integral that I showed you before. And the surprising thing was, after you add these terms, you do it either this way or that way, whatever, the final expression you obtain just has a log. The dialog disappears. In fact, it has a very simple structure of this kind. Okay. And as I said, the dialog or log squared that disappears. And in this way, we come to the title of the talk, which is that it is simpler than the wave function. Now, one complaint about evaluating these things in hard cutoff is that this answer does not satisfy conformal word identities, but you can get around that by working in a different regularization scheme. You can arrive at a regularization. You can work with a regularization scheme that preserves conformal invariance, but it doesn't change the form of the answer. It just replaces lambda, if you like, with k12 plus k34. And it essentially gives you ratios of momentums inside the log. Okay. And in the examples that we have computed explicitly, you observe a similar simplicity for the necklace diagram, which, if you like, is a product of two bubbles in flat space. That's a two-loop diagram. You obtain a similar simplicity for tadpoles and sunset diagram and so on. Now, it's natural to wonder, why does this simplicity occur? Was this an accident in this case? Turns out it's not an accident in this case, although I will explain it just for this simple case. And it is the following. The reason why you have a simplicity here is for the following simple structure of the integrand. So if you look at the wave function's integrand, then you essentially have terms which look like sums of this. You can have some, you have sums of slightly different terms, but they're all of this form. But you have a pole in something like k12 plus k34. E is just that, plus 2L. L is just magnitude of this loop momentum. You can have k12 plus L plus K, and so on and so forth. And since the correlator is obtained from the wave function, you would expect it to share many poles. Both of them almost have the same structure, except that this pole for the wave function gets replaced by just L for the correlator. That is, instead of E plus 2L, you simply have L. And now the nice thing about an integral of this kind is that due to the measure factor, since the measure is d cube L, this pole does not increase transcendentality, because an integral of d cube L divided by L alone is just a polynomial. You don't have, so this in other words, it doesn't give you an extra singularity in the in momentum. And for every example that we compute, you can show that the wave function always has this pole, whereas the NN correlator never has this pole. In fact, this pole gets replaced by 1 over L. And the 1 over L is perhaps not a surprise. If you look at the expression for loop diagrams in flat space, let's say if you look at the bubble diagram, you see that you have an L squared here. And if you imagine integrating the L0 out so that you're left with d cube L, the L squared becomes just mod of L. So that's something you already see in an S matrix. So this sort of hints that the poles of correlators have overlaps with the poles of an S matrix. Okay, and there was some more recent work by Enrico Payer and Donath, where they argued that you could obtain an in correlator from some in-out correlator. It's called the in-out approach, and this is similar in spirit to that. Okay, good. So all these hints sort of led us to this nice formula, which is what I meant in the very beginning, that you could obtain a correlation function from an S matrix, and which is the following formula. So you take an S matrix that you like, and here by S matrix, I mean a Feynman diagram. We don't quite sum up all diagrams, but a single Feynman diagram. And you essentially attach some, what I'd call auxiliary propagators, and you integrate over them. So this is the integral transform that I talked about at the very beginning. So you take an S matrix and you perform an integral transform of that object. And that leads to the following, to the in correlator. So this sort of suggests an inverse LSE formula where you're obtaining a correlation function from the S matrix. Okay. So just to give you an example of this in practice, because this was quite formal, you can take the bubble diagram in flat space, and then you attach these two propagators. So what I'm denoting by R here is basically denoted by these red propagators, and you integrate over these P1 and P2. Okay. And the exact structure of these R's, they are theory dependent. But for the case of interest, let's say for 5-4 theory, R just looks like this. It's 1 over P squared plus K external squared. So if you have a diagram like this, where you have these extra R's, you take your flat space bubble diagram, which is integral d4L by L squared L plus K whole squared, and you attach these two auxiliary propagators, R of P and R of P prime. Then you integrate out P prime by the delta function, and it basically looks like this. And evaluating this integral gives the expression that I showed you before, which is just a simple log. Okay. And in fact, you can argue in general how the result of these P integrals should look like, but the basic idea is that you take any flat space Feynman diagram and you sort of integrate over the energies of the external particle with some auxiliary propagators, auxiliary one-dimensional propagators, and the fact that it's one-dimensional makes the thing much simpler. So you integrate against some auxiliary one-dimensional propagators, and that gives you the in correlator. And if you like, this can also be recast as the statement that you take an S matrix in flat space and you just compute an integral transform of that object, and it leads to a correlation function in de Sitter space.
So that statement is now more or less at the level of a theorem, right? So the formula which you showed on the previous slide, I can view it as a theorem.
Yeah, good. So we have a proof of this formula. I mean, we in this paper from December with these set of authors, we sort of proved it to two loops for conformally coupled scalars, where we even checked that the theory was renormalizable, like 5-4 theory was renormalizable in de Sitter. We even checked that. We think we have a proof at any general order in perturbation theory for more general interactions, including interactions which leads to IR divergences. But it's not yet, there are still some loose ends to tie up. But the expectation is that there's always some dressing factor like this, which is that you take a flat space Feynman diagram, and in this example, I've shown it for a loop level diagram, but it's also, of course, true at tree level. You just take a flat space Feynman diagram, you attach some auxiliary propagators, which conserves energy, and that computes a de Sitter correlator for you. So this general idea is still true. In order to convert it to a theorem, we still need to specify what this auxiliary propagators are for more general theories. But up to some technicalities, yes, indeed, I think it can be viewed as a theorem.
I see. Thanks.
Good. And yeah, for this example, as you see, for conformally coupled cases, which is, if you like, the cases where you can easily map it back to flat space, you essentially integrate over things which are Lorentz invariant. So these R of P's just look like this, which factors out of the loop integral. There are cases like the minimally coupled scalar, etc., which are not conformally coupled and so on. But for that case, this R of P also has terms that don't look Lorentz invariant, but there's still a systematic way to always attach some propagators and obtain an answer which works. Now, this kind of a thing is true for the Indian correlator. And you might ask whether a similar representation was also true for the wave function. Just to recap, you could ask whether we could obtain this thing, the wave function, from a similar representation where you take the flat space as matrix and you attach some propagators, which upon integrating gives you that result. And the answer is yes, you can do it. But in general, the wave function has more complicated denominators. So here, for example, FIFO theory, you just have a very simple denominator, which is like a one-dimensional propagator. But for the wave function, you get some other terms in the denominator, which does not make the structure as simple. Okay, good. Good. So now let me conclude. I think I'm well ahead on time. So all this calculation shows that there is a hint of some simplification in objects beyond scattering amplitudes. So usually most of the simplification that we have seen in the amplitudes program till now was very limited to computing scattering amplitudes, which of course is something that most people are interested in when it comes to collider physics experiments and so on. But if you were interested in cosmology or ADS-CFT, then the correlation functions in ADS and so on are not usually very simple to evaluate. So you need better tools, and I think we now seem to be doing slightly better than we were 20 years ago. So this is a hint of that. And then many tools that you use for studying scattering amplitudes can be generalized to also compute correlation functions in ADS or DS. Some examples include the integration by parts technique. I didn't emphasize on that much, but in flat space, the integration by parts technique often helps you evaluate loop integrals. So there were many novel loop integrals which could be evaluated by using integration by parts. And in ADS and DS, we use that to obtain recursion relations and various other things. Then this also provides a way to find answers that are manifestly de Sitter invariant. In other words, the answers which satisfy conformal word identities. You can write down regularization schemes which do it. And one main takeaway from this talk is perhaps that if it could be summarized, which is that cosmological correlators have simpler poles than the wave function. And because of them having simpler poles than the wave function, it means that they often lead to integrals which have lower transcendentality. And this statement can also be viewed as de Sitter correlators are simple or are simpler than ADS correlators. Good. And the other conclusion we have is that this inverse LHC-like formula that I just described helps you evaluate some object in curved space from an object in flat space. And this also works for spinning cases. It seems to be working for at least for Yang-Mills theories and so on. And perhaps one nice future direction, of course, is how to better study integrals is I think a question which many people are interested in. And like I said, there are these differential equations techniques which exist in flat space, and they have more recently been used to analyze cosmological integrals. And I think that's an interesting approach, which could be applied to this new formula that we have here. Whether you can analyze these new integrals using some differential equations. And since you have representations of this kind, you can also ask questions that relate that are about cutting rules. We study cutting rules and the optical theorem in flat space, and it's a natural question now to ask whether you can use that in de Sitter. Okay, so thank you. I'm done with the talk.
Thanks very much, Chandramouli, for this very nice talk. Thank you.